It's a really great pleasure to be here to open the Future of Computing session. And when you see the lineup of myself and my two colleagues who are speaking, it might better be called the Future of Computing is Quantum. And I happen to believe that. And so before I kick off, we've heard a bit of talk about quantum computing already this afternoon in our sessions. But I just want to emphasize a point that I think is really important. I think everyone in this room accepts that this computer here obeys the laws of physics at all levels of its operation, right down to the nanoscale. There's a skeptic at the back there. And that's also true of anything else in the world, obeys the laws of physics. And a pretty natural corollary of that, if you like, is that if the laws of physics were different, then what it was possible to compute would also be different. Another hopefully uncontroversial statement is that this machine right here does not harness quantum mechanics in its core operation. So, in fact, you need a quantum mechanical description of it to understand it at its most fundamental level. There are no semiconductors in classical Newtonian physics. But nevertheless, it doesn't harness the unique properties of quantum mechanics for its operation. And so a further corollary is that if you did harness quantum mechanics for computation, you might be able to access a different class of computation, and that is indeed true. And I'm going to elaborate on that over the next 15 or 20 minutes. So this is a talk that I gave earlier this year at the World Economic Forum in Davos. And the thing that really struck me there is the transition that's happened with quantum computing again. So I think there's been a few transitions. Up until about 5 years ago, it was a bit like what we heard in the last session. It's been 25 years away. It's been 5 years away for the last 25 years, and that's always been true. And I think about 5 years ago, the popular story in the press transitioned from being crazy quantum physicists in some dark laboratory somewhere, Einstein's spooky action at a distance, entanglement, weirdness and wonder. That was the story. And I think probably about 4 or 5 years ago, the article in New Scientist that really struck me was the quantum computer that Google bought doesn't do the job to train Google Glass. And to me, that marked a real transition to, from if to when. And what I observed earlier this year was another transition, which is that CEOs of Fortune 500 companies and heads of state have largely heard about quantum computing and are interested to know what the impact is likely to be. And so maybe you've seen this video, which went somewhat viral, of the Canadian Prime Minister answering a question from the press on how a quantum computer works. So I think that really tells us a bit about where the world's moving. So what I'd like to do is give you a flavour of how it might impact your businesses. And it's a real pleasure to be able to speak to the technical leads from the array of companies that we have represented here today. And I'd like to start by just giving you a quick synopsis of how I got here. A long time ago, when I was a wide-eyed undergraduate student, I bought this magazine, and I read about how if we could build a quantum computer, we might be able to bring about a revolution akin to the agricultural, industrial, and digital revolutions. And at the time, I thought that was pretty amazing, and I happened to be studying quantum mechanics for the first time and found that also pretty amazing. And the confluence of the two of these facts led me to continue in the field of physics and ultimately to travel from one side of Australia to the other, from one side of the world to the other twice, and in the process build a research team of around 100 people. And what I'd like to do is share with you why I'm so passionate about this task of building a quantum computer. So I don't think there's any controversy here when I say that nothing has transformed the world more than our ability to compute. From vast data centers conducting commerce at all scales to mobile phones conducting commerce in marketplaces in villages in the developing world. And I think that we've already heard a lot, particularly in the last session. I think if you polled the average person, they would probably say we've had a computer revolution. And I think a lot of us in this room would contend that we've barely even begun that revolution. The things that we're going to do with big data and machine learning and so on are very profound. We're going to discover new cures for diseases on the basis of vast quantities of data from individuals and populations, and so the list goes on. Again, I think all of you in this room know the story of how we got here, and that story is Moore's Law. And I don't want to tell you things that you already know, but I'd like to amaze myself once again and perhaps enthuse you to continue to be amazed by this story. Moore's Law is humans traveling up an exponential curve for half a century. That should be impossible, right? It should be impossible to do that. And it has only been possible because of the trillions of investment that have gone into it and some of the smartest minds in the world that have gone into it to keep that tracking along because of the economic imperative. And I would contend that at the end of that journey, our ability to process silicon is science fiction-like. These silicon wafers that you see here each contain hundreds of chips, each with billions of components in them, and we produce billions of those chips every year. And I think the impossibility, the seemingly impossibility of this task is typified by the fact, and there are many people in this room, I'm sure, if you worked in the semiconductor industry at any point during that half century and you had said that what was ultimately possible a decade later would be possible, you'd be laughed out of a job. So at every step of the way, we'll never get below 1/4 of a micron. We'll never get below 100 nanometers. We'll never get below 10 nanometers. And so the story goes. So despite retrospectively knowing that those predictions were foolish, I'm going to make another one here today, and it's been alluded to already, and that is that we will never make transistors smaller than the scale of an atom. We won't make subatomic transistors. So I'm on record as having said that. And so there is a fundamental limit coming to Moore's Law, and already if you look at the smallest feature sizes in state-of-the-art computer chips today, you can count the number of atoms across those smallest feature sizes. And yet, this is not what I want to talk about, the end of Moore's Law, because even if Moore's Law was to continue indefinitely, there are still problems across artificial intelligence, the design of new materials, clean energy devices, pharmaceuticals, finance, and the list goes on. There are problems that we would never solve with any conventional computer. So even if we took every silicon atom on our planet and turned it into a giant supercomputer, we would not solve these and many other important problems. And the good news is that if we were able to make a computational machine that harnessed quantum mechanical properties, we could solve these and many other important problems. In fact, if you look across all of science and technology, you'll find problems that quantum computers are extraordinarily good at tackling. And I think before I get going and talk through some of these to you, I'd like to emphasize that this is really not faster computation. This is redefining what it is possible to compute, because I would say that if factoring a many thousand-digit number takes a supercomputer billions of years, that is not possible to compute. And if it takes a quantum computer minutes to answer that question, then it is possible to compute. So I think there's maybe a conceptual mistake there in thinking of quantum computers as just being faster computers. It's really a redefinition of what's possible to compute. So I want to start and survey just a couple of key areas that might be of interest to you. Firstly, in that chemistry space, and then in the computing space, and a little bit in the healthcare. So Richard Feynman, the late great physicist, really initiated the whole field of quantum computing with his contention that it's impossible to simulate a quantum system on any conventional computer we will ever build. And the reason for that is reasonably straightforward. If we were to write down the state of this molecule, say it's got 6 atoms in it, then it might take us a page of paper to write that down. And then if we add an atom to that molecule, we would need 2 pages of paper to write it down, and then add another atom and 4 pages, and so it goes. And this exponential growth in just describing the molecule prevents you from doing any useful computation on it in an exact way, which is what you ultimately need, chemical precision, to know what the properties will be. And so one of my favorite examples of this is nitrogen fixation. So I'm sure in this audience, most of you are aware that half of the nitrogen in your body is probably produced in a factory through the Haber process. We simply couldn't feed the world's population without the advent of nitrogen-based fertilizers. And that process is one that consumes something like 5% of the world's natural gas production and a similar amount of the world's energy production. It's a process called the Haber process that was invented about a century ago, and despite the obvious economic imperative for doing so, we haven't been able to improve upon that, despite the fact that we know that it's possible because there are microbes in the soil everywhere doing the same thing in ambient conditions. And so with a quantum computer with 1 to 200 logical error-corrected qubits, and I'll come back to what I mean by that, but with a universal quantum computer of that sort of scale, we could start to address this problem and come up with more efficient mechanisms for doing that. And similarly, with a quantum computer of maybe twice that size, so with 200 to 400 logical error-corrected qubits, we could start to address catalysts for carbon capture out of the atmosphere. In fact, I would say that in the future, it will be the design of new molecules and new materials that really underpins our existence on this planet. It will no longer be good enough for materials to just serve a single purpose, structural. They should be structural, energy harvesting, energy storing, part of the communications network, part of the sensing network within those systems. And we've heard about graphene a couple of times today, and I think it will be necessary for us to invent many dozens of wonder materials like graphene in a world where we have finite resources, and the imperative for deploying them parsimoniously is just ever increasing. So designing new clean energy devices, new polymer membranes for fuel cells, and so the list goes on. A very exciting area, I think, again in molecular design, is designing new pharmaceuticals. So all of the same issues that I just described concerning molecules apply to the molecules that we use for pharmaceuticals, and indeed their interaction with the human body. And furthermore, in genomics, the problem of pattern matching is one that we deploy vast supercomputing power for, and it turns out that a quantum computer is particularly good at that. And so quantum computers, I'm convinced, will do wonderful things for us in terms of molecular design and simulation. But I'd like to now talk about the area of artificial intelligence, not for too long, because I think the previous session on the future of digital could have also been called The Future of Digital is AI. And it turns out that if you pick up a machine learning textbook and you go through the table of contents, we now have an emerging understanding of how to do all the tasks that are listed in there better on a quantum computer. In some cases with a constant prefactor, and in some cases with a double exponential increase in speed. So I hope Ali might say this directly, but I'm pretty sure that Google gave the provocation that there won't be any AI in the future. There'll only be quantum AI, because why would you do it any other way? But I'll leave it to him to say that if he should so choose. Now, I would be irresponsible if I didn't mention the issue of security. Many of you in this room are ultimately responsible for security within your organizations. And so suffice to say, quantum communication systems exist today. Quantum money and quantum verification is on the way, and you've no doubt heard that the factoring example that I gave you right at the beginning renders most of the current encryption schemes that we use today inoperable, ineffective. And so I'd like to just finally tell you a little bit about how your personal life might be affected by painting a little bit of a picture of what your life might look like when we have these things. So imagine now that your mobile phone, you can't really draw the boundary between the sensors and the battery and the communication systems and so on. It's wonderful new materials that we've designed on there that couple directly to sensors, biocompatible sensors in your body, and that whole system monitors your state of health, physical and mental health, in extraordinarily intimate ways, such that the information that it generates is extremely private. You'd like that to be communicated to your doctor securely, obviously. Your doctor might then use the aid of a quantum computer in the genetic analysis that is required to be done to make a diagnostic on you, and indeed might use artificial intelligence techniques on that same machine to make that diagnosis, prescribe a pharmaceutical that has been a molecule that's very specific, designed on that same machine or a similar one, and indeed encapsulated in some material that enables it to be delivered to the target very efficiently. So that's a vision of the future. So given this wonderful vision, where are these things? Why don't we have them already? And you're about to hear, I hope, from my colleague at D-Wave about a wonderful approach to building special purpose devices without error correction. But the majority of the tasks that I've talked about here require a large-scale universal quantum computer. And it turns out that the overhead for error correction in those devices is very, very large, something like a factor of 10,000. And the reason for that is pretty simple. Quantum computers are a hybrid digital analog system. And there are very good reasons why we don't have large-scale analog conventional computers, right? They're just error-prone. Noise propagates. And so you pay a big price in correcting for those errors. So the task ahead is to go from the few qubits, so the dozen that are in labs in Google, in IBM, and academic groups around the world, to something like 1 million qubits in order to make that several hundred logical qubit quantum computer. And that is a considerable task, because if you think each of those qubits is composed of a handful of components, then you're talking about a large-scale integrated system with millions to billions of components all coherently operating together. And so for me, there's some important definitions here, and they are about feasibility, scalability, and manufacturability. So feasibility is, by my definition, something about the mathematical in-proof of principle. We don't need exponential resources to make this quantum computer. Scalable is that it's modular. You have a design that you don't have to overhaul and start from the beginning each time you scale the system up by an order of magnitude. Pretty standard definition. And manufacturable means that we realistically have the tools to make it. And so I would say that you could build you could have a scalable architecture for a quantum computer that was the size of this room. I'd sampled from the whole periodic table. I'd specified where every atom in the molecule went. And I would say that's not manufacturable, not because it defies the laws of physics to manufacture it, but because the facility that we would need to make it might cost more than the GDP of the planet by many orders of magnitude. I'm being deliberately provocative and facetious on that point. So let's imagine we could use this technology to make a quantum computer, this science fiction-like capability to fabricate billions of components in silicon. Well, we've figured out how to do that, and if you'd like to learn more about that, please come and talk to me. Thanks very much.